These are the species we draw. And if we were to evaluate this reaction at equilibrium, this is 4.75. And some of you guys might have seen hydronium ion in the table while you were studying or doing some of the book problems, but we're not going to memorize this particular number per se, but hydronium ion is the strongest possible acid in water. We should know at least that it's a very strong acid. So we have a weak acid and a strong acid, and we know that the equilibrium should definitely be favoring the reactants if we were to take into account this idea that this is a very strong acid and this is a weak acid, a relatively weak acid. This particular equilibrium equation, KEQ, is often written as Ka, right? The acidity constant, and it really involves the concentration of the conjugate base and hydronium ion over the reagents, which is the acid in our case, and water. This is often reduced or simplified quite a bit because water is in excess and its concentration doesn't change very much, and it's often just related to the concentration of the conjugate base times H3O plus over the concentration of the acid. And for carboxylic acids, this particular number, the Ka, is about 10 to the minus 4 or 10 to the minus 5. It's a very, very small number. This very, very small number tells us that at equilibrium, we have mostly these things. This number here is less than 1. That means the concentration of the acid is much higher than the conjugate base or hydronium ion. In reality, at equilibrium, there's about 1.3% of this ionized acetate. So the reaction really is favoring at 88.7% or 98.7% these starting reagents. So these are weak acids. They don't fully dissociate. It's not like HCl or HBr or H2SO4. But this is literally what a pKa of 4.75 means. It means the Ka is about 10 to the 4, 10 to the 5. These reactions still favor this particular direction. And this is a review from Gen Chem. But if it's confusing, don't panic. We're going to do this activity about 4 or 5 times together today to try and understand why this is 4.75 and why an alcohol is 16. We're going to use induction, we're going to use resonance, and we're going to use the stability of the corresponding conjugate base to understand this phenomenon a little bit better. So we're going to do a lot of same examples over and over again today. This will help us learn and prepare our minds for these types of activities. Ka is the acidity constant. And then we have a large Ka, we will have a small pKa, and we will have a stronger acid. Okay, so as the pKa goes down, we already know that this makes stronger acids. Okay, it really means that we also have a large Ka, right? If we think about that, Ka equals the concentration of the conjugate base times acid over the concentration of the starting acid in our last equation. So as this number gets very, very big, the acid, which is on the left side of the equation, dissociates and we get more and more proton, more and more conjugate base. And so as this number gets big, it means we have very, very strong acid, which is fully dissociating, and these concentrations are growing and this is decreasing. And the way Ka works, it's the negative log. So we get, or pK is the negative log of Ka, so we get small numbers that are easier to work with. So smaller this goes, the better. Let's actually just redo this, and we're going to keep using water to understand a little bit about why something's a strong acid, why something's a weak acid, and water is the perfect medium or solvent, or it's going to play the role of base in all of these examples, so it'll help us understand where these numbers come from. We're going to waste a perfectly good molecule of ethanol this morning. We're going to react it with water. And right away, we can tell that these have very, very similar pKa's, but we're simply going to use water as a base in all of these cases to kind of look at what happens and why some compounds are more acidic than others. So the most acidic proton we have in the ethanol molecule is the OH bond, or the OH proton. It's not the CH2 or the CH3. And we'll use water as a base. we're going to evaluate ethanol in the context of it serving as an acid. We draw these same two arrows. You should be very good or getting much, much better at this. And then we're going to draw the resulting conjugate base of our acid and the conjugate acid of our base. The arrows in red explain how I'm drawing this and why I'm drawing it this way. Proton's gone. It's been broken. There's 3 pairs of electrons around oxygen. It had 2. This bond breaks. The electrons come back. So we get the conjugate base of ethanol. It's known as ethoxide. And as water's picking up a proton, as indicated with this first arrow, it's making a new bond. That bond breaks. We should have 3 bonds to water. And we get to hydronium ion. It's very similar to what we did in the last example with our carboxylic acid. Okay? We just switched the things and moved things around. And we know that the pKa of this is 16. Okay? It's about the same as water. It's not terribly acidic the last time I drank it. And this is hydronium ion, a very strong acid. So this is a weak acid, strong acid. At equilibrium lies this particular direction. Let's contrast and put on the same page the reaction we just did moments ago. We're going to just take acetic acid again. We'll keep doing this with acetic acid a couple times. The fact that I'm doing it a lot means that you should be prepared to do it for our exam. Carboxylic acids and this particular property of them, that they're acids, is important. And then we're going to have this equilibrium box. We already know the direction. It's going to favor the reactants. We'll draw the conjugate base, which is acetate. We'll draw hydronium ion. Hydronium ion is a much stronger acid than acetic acid, which has a pK of about 4.75. So again, the equilibrium lies back to the left. Again, this is just repeating what we just put into our notes previously. It's important that it's here again. Sorry, things are a little sloppy. I'll try and clean it up a little bit. But we know that we have the same OH group here, but there's a drastic difference in pKa between these two things, and that's the key point, focal point of our lecture today, and it's based on 2 phenomena that are important for us. One's the inductive effect, one's the resonance effect. To understand resonance and inductive effect, we're going to spend some time carefully examining the stability of conjugate bases. This is where we're going to turn our attention to understand the difference between these two things, which may not make much sense to us. One of these two things is much more stable than the other. One of these two things is much more stable than the other, and our pre-lecture video should prepare us to understand this already. We talked about in the pre-lecture video that this particular bond is polarized. There's delta plus charge here, and right next to it there's negative charge. This combination of factors is known as induction, and the slight partial positive charge that's built into the dipole of this carbonyl group is close by to a negative charge, and it helps stabilize it. This species is much more stable than this one above it. Here, this is nonpolar, nonpolar. Here, this is very polar, putting partial positive charge on the carbonyl group. That helps stabilize this negative charge. In turn, it makes this equilibrium slightly more favorable this way. In turn, it makes this particular bond easier to break than this one. We can also see it in this particular molecule. We still see there's delta plus right here, delta minus here, dipole here. But the other way to see it is, rather than looking at the stabilization of the products, we just look right here. This bond is the one that's going to break. And it'll be easier to break this bond if electron density is being pulled away from it through the carbonyl group. Okay, this is what the slides, we had a slide like this with some arrows on it last night to look at. That's kind of the important point about those things. So we'll revisit and keep talking about induction. The other phenomenon that we can discuss is resonance, and we're going to very briefly talk about resonance.